In this video, let us learn about linear span of a set, or I can say subspace generated by a subset. Subspace generated by a subset. Suppose I have a vector space V be my vector space over a field F, and S is any subset of V which may be empty or non-empty. Okay, if S is any subset of a vector space V, may be empty or not, then the subspace generated by a subset is denoted by either L of S or S, like this, is nothing but intersection of all subspaces of a vector space S, where W alpha is a subspace of V. In fact, this is the smallest subspace of V containing the subset S. Containing the subset S. I have a vector space V which is defined over a field F, and suppose S is any subset of V, then subspace generated by S is defined as intersection of all subspaces of V, and it is denoted by denoted like this, or you can even denote it by L of S. In fact, see, if I have, in general, suppose I have any vector space, I'll denote it like this. Okay, this is my vector space. I have a small set, say yes. Okay, then I can have a subspaces, say subspace 1 W1 W2, like this. They are the subspaces containing S. Okay, say this is W1 and say this is W2. These are the subspaces containing S, and this S is the smallest subspace of V which is containing S. S is any subset, and these are the subspaces containing S, but this S itself is the smallest subspace, and this is called subspace of V generated by S. In fact, so you can know things. Suppose if I have a singleton, if I have a null set pi, then this is say 0 vector in this. This is a subspace of V containing phi. Okay, and if I say if I have a subspace generated by a 0 vector, this has got simply 0 vector. This is a subspace generated by phi. In the sense, if I have any vector space V, then 0 vector is in, this is the set which is having 0 vector. Okay, only 0 vector. Then these are the subspaces containing the set. So set S is having only 0 vector. Subspace generated by this 0 vector is a smallest subspace containing S, where S is 0 vector. Okay. Before giving another example, just look at the nature of this L of S, or subspace generated by L of S. Suppose I have a vector space. Let V be a vector space over the field F, and S is a subset of V. Then this L of S we call linear span. Why? Because it's a set of vectors V such that each vector in V is a linear combination of vectors AI, Vi, where AI belongs to the field F and Vi are the vectors from the subset S and n is greater than 1. See, if I have a vector space V over a field F and S is any subset of V, then L of S is nothing but set of all those vectors, which is nothing but the linear combination of vectors from the subset S. In this sense, if I take this as any set, say W, W is set of all linear combination of vectors, then I have to show that W is a subspace and that W itself is L of S. L of S is a linear span, or I can say subspace generated by S. So first thing I have to prove, I'll take this linear combination of vectors as W and I'll prove it's a subspace. Once it is a subspace, then I have to show W is nothing but L of S, or L of S is nothing but W. Okay. So let me take, let W be my set in such a way that in that all the vectors are nothing but the linear combination of vectors 1 to n, where AI is from the field F and Vi belongs to set S and n is greater than 1. Okay, I have to show that this is a subspace. Once this is a subspace, then this itself is L of S. If I show that, then it is fine. Okay, so this is a theorem which states if V is a vector space over a field F and S is a subset of V, then L of S, this is a subspace. Okay, so first I'll just take W and I'll show W is a subspace. After show this, W is a subspace. So let me take two vectors from V. Let V and V dash, from W, let V and V dash belongs to the set W. And how is V? Any vector in W is a linear combination of vectors from S. Okay, so V is AI, Vi, where I ranging from 1 to n, say, and AI belongs to F and Vi is from set S. Similarly, I'll define V dash. Any vector V dash is, say, Bj, Vj dash, where j is ranging from 1 to m. Such just a notation. Okay, Bj is from the field F and Vj dash are from the subset S. Now to show any set of vectors is a subspace, first I have to show the linear combination, whether vector addition and scalar multiplication belongs to the set or not. Okay, so let me take V dash. If I take this, then this is AI, Vi, I from 1 to n minus summation Bj, Vj dash, j ranging from 1 to m. This is same as writing summation AI, Vi plus summation minus Bj, Vj dash. You have to write the range. Okay, in fact this belongs to W because vector addition can be explained like this, can be written like this. So V minus V dash belongs to W, then I have to check for alpha V, alpha or A, whatever, it's for some scalar. A. For any scalar, say alpha belongs to F, if I consider, then alpha V is nothing but alpha into summation AI Vi. I have to write the range, which is nothing but summation alpha AI into Vi, which is again a linear combination of vectors. So therefore I can write it belongs to W. So I can say W is a subspace. So one part is over. Then I have to show L of S is nothing but W. Okay, so for that I have to show L of S is contained in W, and I have to show W is contained in L of S, so that W becomes L of S. So since I know that, since for any vector V belongs to S, 1 in V is nothing but 1 into V, right? So this V belongs to W also. V is from S. For any vector in S can be written as 1 into V, so that vector belongs to W, which is linear combination of vectors can be expressed like that. Therefore I can say that this S is contained in W. So how is any vector in S which can be written as a linear combination of vectors? So this is nothing but L of S. L of S is contained in W, because this L of S is the smallest subspace containing S. It's the smallest subspace containing S, so therefore it has to be contained in W. Okay. The second part is I have to show W is contained in L of S. So now let W dash be any subspace containing S. There is one more subspace, say W dash, which is containing S. Now for any vector V belongs to W, V can be written as linear combination of vectors. I have to write the limits everywhere for the summation here. Okay. So Vi belongs to S. Hence I can write V also belongs to W dash. So W is any subspace containing S, and every vector in W can be written as linear combination of vectors in S. Since each Vi belongs to S and S is, therefore I can say S is contained in W dash. Therefore I can say that W dash is a subspace, and I can say W is contained in W dash. Okay, so I can write W is contained in W dash, and I can also write W is contained in L of S. Therefore from here I have proved L of S is contained in W. Here I am getting W is contained in L of S. Therefore I can say W equal to L of S. So now look at the example. Suppose I have a vector space V, say R2 over R. I have two subsets, say S1. Say this is set of all two tuples 1, 0. This is one subset, and say this is another subset, which is say 1, 0 and 0, 1, suppose. Okay. Now I have to find the subspace generated by this S1 and S2. I have to calculate this. find subspace generated by S1 and S2. So how is any element in R2? R2 is nothing but R cross R. So any element in this is of the form x comma y, right? So first set S1 is 1 comma 0. I have to find the subspace generated by this. So for any alpha belongs to the field F, here the field is set of all real numbers R. So for any alpha belongs to R, alpha V, the vector I'm taking, it is in the form 1 comma 0. I have to check for vector addition and vector scalar multiplication for the vector. Here only one vector is there, so I'll directly go for scalar multiplication. What happens when I multiply that? Alpha into V is alpha into 1 comma 0, which will be alpha comma 0. So the subspace generated by this set S1 is alpha comma 0 for where every alpha belongs to the field R here. Okay. In fact, what is this? When I take, say, R square, R2 means entire x-axis and y-axis. When I take this set, I'll take any scalar from the set of real numbers. I'm getting subspace generated by that as alpha comma 0. How is this? 1 comma 0, when I take x value is 1 and y value is 0, right? Alpha comma 0 means any value on x-axis but y value is 0. So this entire line is the subspace generated by S1. Okay, this entire line. Simply the subset is just 1 comma 0. This, okay. But subspace generated by 1 comma 0 is entire x-axis. Similarly, for the second set S2 is having two vectors 1 comma 0 and 0 comma 1, right? So I'll check for vector addition and scalar multiplication. Suppose I have alpha beta from the field F. Here the field is set of real numbers. So alpha V1 plus beta V2, alpha into, this is V1 V2, I'm taking like that, plus beta into 0 comma 1, which will be alpha comma 0 plus 0 comma beta, which is nothing but alpha comma beta. Therefore, the subspace generated by H2 is set of all alpha comma beta such that alpha beta belongs to the real number set. In this case, this is in fact nothing but x-axis. Okay, here what happens when I take this 1 comma 0 is here, 0 comma 1 is here. Okay, it has got, S2 has got only two vectors 1 comma 0 and 0 comma 1, but the subspace generated by S2 is alpha comma beta. It can be here, can be here, here, on this line, anywhere it can be, because alpha beta belongs to set of real numbers. Therefore, this is a subspace which is nothing but entire xy plane. Okay. Now let us learn one more nature of subspace. Suppose I have a vector space V over the field F, and I have two subspaces V1 and V2 of a vector space V. Then if I add two vector spaces such that one vector in W is nothing but sum of the vectors in two vectors, then the set forming by adding two subspaces is also a subspace. I have two subspaces. If I add two subspaces, I'm getting a new set, and I have to show that this is also a subspace. Okay. Let me take two vectors, say v and v dash from W. I have to show W is a subspace. So that what happens, how is any vector in W? By definition, any vector in W is sum of the vectors from the two subspaces such that v1 dash belongs to v1 and v2 dash belongs to the subspace v2. Then I have to, for showing W as a subspace, I have to show I have to check for the vector addition and scalar multiplication. V minus v dash. So it's not necessary that you have to take v minus v dash only. If it is a particular example, then we go for vector addition. Okay, if it's in general you are proving, then usually we prove this. Okay, if this is true, then obviously addition will become true generally if I consider. But I have to check this also. So it's better go for checking this only. If this is true, then obviously the addition will belongs to the particular set you are checking. Okay, if it's a particular example, then you directly go for vector addition. In general, if you are proving, then take for the subtraction and show. Okay. V minus v dash. What is v? V is v1 plus v2, and v dash is v1 dash plus v2 dash, which can be rewritten as v1 minus v1 dash plus v2 minus v2 dash. Again, it is sum of the vectors, so that this belongs to v1 and this belongs to v2. Therefore, I can say that v minus v dash belongs to v1 plus v2. No problem with vector addition. Now, for any alpha belongs to F, field F, alpha v is nothing but alpha into v1 plus v2, which is nothing but alpha v1 plus alpha v2. Again, this belongs to v1 because v1 is a subspace. This belongs to v2 because v2 is a subspace. Therefore, I can say alpha v, this belongs to sum of the subspaces v1, v2. So, vector addition and scalar multiplication is true. Therefore, I can say that v1 plus v2 is a subspace of v. Subspace of v. Next is direct sum, which is just an extension to this vector addition. Addition of two subspaces. Suppose I have a vector space V which is defined over the field F, and I have two subspaces V1, V2, two subspaces of V. Then V is called a direct sum of V1, V2, which is denoted by V1 direct sum V2. The vector space V is called direct sum of two subspaces if I have V as V1 plus V2 and intersection of these two subspaces singleton 0. If I have two subspaces V1, V2 of a vector space V, then I can say V as a direct sum. This is the notation, direct sum of V1, V2 if V is V1 plus V2 and the intersection of two subspaces is singleton 0. So let us look at the nature of this direct sum. So there is a condition that if V is a vector space and V1, V2 are the subspaces of V, then I cannot say all the addition of two subspaces gives me the direct sum of V. Okay, so there is a condition. The condition says if I have a vector space V, to say that it is a direct sum of V1, V2, if every vector in V can be uniquely expressed like this. Okay, if every vector can be uniquely expressed like this, then I can say that V is a direct sum of two subspaces. Okay, let us prove this. I'll take first part. Suppose V is a direct sum of V1, V2 and every vector can be expressed like this. I'll just show the uniqueness. I have to show the uniqueness of this expression. Okay. Suppose V is a direct sum of V1 and V2 and every vector V belongs to V can be expressed like this. V is V1 plus V2 such that V1 belongs to subspace V1 and V2 belongs to subspace V2. I have to show the uniqueness. This expression is unique. Okay, I have to show that. For that, I'll take one more expression for V and then I'll show that expression and this expression is same. Okay, so let V can also be expressed as V is also equal to say V dash, or here I have taken V1, so let me take V1 dash and V2 dash. I mean to say V can also be written like this, suppose, and if I end up showing this is equal to this, then no problem. So I'm saying this V, vector V, can also be written like this in such a way that V1 dash belongs to subspace V1 and V2 dash belongs to subspace V2. Then now V is equal to V1 plus V2, which is equal to V1 dash plus V2 dash, right? So if I take some vector, say W, in such that it is nothing but V1 minus V1 dash, and which is same as writing V2 minus V2 dash. Okay, say I'll write this, can also be written like this, V1 minus V1 dash, which is same as writing V2 minus V2 dash, right? Or V1 minus V1 dash, V2 dash minus V2. Okay, now this as the element, say I'll call this as equal to, say, some element W. Okay, now this is the element which belongs to the intersection of V1, V2. Why? Because say this entire vector is in the subspace V1 and this entire vector is in subspace V2. So there is one such element, say that I'm calling it as an element W. They are in V1 and in V2 also. Therefore, I can say that this element belongs to intersection of V1, V2. I hope you got it. See, V is equal to, it has got two notations. I'm considering it like that. Okay. Now, I'll take up only these two. Okay. so that v1 minus v1 dash, which will be equal to v2 dash minus v2. Simply I'm rearranging this equation. Okay, now say this is a vector from v1 and this is a vector from v2. So there is one vector, I'm calling it as w, which is in v1 also and in v2 also. Okay, so I can say that that particular vector which is in the intersection of v1 v2. Okay, now in fact I know that v is a direct sum of v1 and v2. Therefore, by the definition of direct sum, element in the intersection of two subspaces is 0. Since I know that by the definition of direct sum, intersection of v1 v2 has only one element, that is element 0. Therefore, this w has to be equal to 0. W is equal to 0, which implies if w equal to 0, then v1 minus v1 dash is equal to 0, which is nothing but I can even write v2 dash minus v2. v1 minus v1 dash equal to 0 implies v1 equal to v1 dash. v2 dash minus v2 equal to 0 implies v2 dash equal to v2. What happens then? I have taken this v has got another representation saying v1 dash plus v2 dash. Now I end up saying v1 dash is equal to v1 and v2 dash equal to v2. Therefore, this is equal to v1 and this is equal to v2. Therefore, the representation v equal to v1 plus v2, this expression is unique. The first part is over now. I have taken v as a vector direct sum of v1 v2, and if I represent any vector like this, I am showing that this representation is unique. Now the converse part is I have to show if this is the case, then like if a vector is uniquely represented like this, then I have to show it as a direct sum of v1 v2. So conversely, assume that v is a vector belongs to v and has a unique representation, uniquely expressed as, say, v equal to v1 plus v2, such that v1 belongs to subspace v1 and v2 belongs to subspace v2. Then I have to show that v is a direct sum of v1 plus v2. Okay, for that I have to show intersection of v1 v2 has only one element, that is 0. Okay, so I have to show intersection of v1 v2 has only element 0. For that, let me take there is an element w in v1 intersection v2. Okay, I know every vector I can write, every vector in v can be written as sum of the vectors from v1 and v2. Okay, so I'll write this as, say, w plus 0, so that w belongs to v1 and 0 belongs to v2. Okay, since v2 is a subspace, of course it has got 0. Similarly, I can write w as 0 plus w, right? So that 0 belongs to v1 and w belongs to subspace v2. Now, by the uniqueness of the expression, see, I have already taken that every vector can be uniquely expressed as v1 plus v2, right? So, by the uniqueness of the expression of w, by the uniqueness of the expression for W, what I'm getting, W equal to 0. Vector is uniquely expressed like this, therefore W equal to 0. So that element is 0 element itself. Therefore intersection of V1, V2 has got only one element, that is 0. Therefore I can say that V is a direct sum of V1 plus V2.